Good morning, everybody. Wow, the keynote really got you all jazzed up, didn't it? Morning, everybody. It's a lot better. Still not great, where the keynote either just exhausted you with all the cool stuff that we announced and showed you. How many people have been to Build before? Just out of curiosity. Okay, pretty good repeat audience. How many people have written an application for Azure before? How many people are writing applications for Azure right now as part of your job? Okay, target audience, that's good to see. Welcome to Building Applications for Azure Lessons from Scale. My name is Mark Arsinovich. I'm CTO from Azure. And what I'm going to share with you in the next 60 minutes are some tips on how to design an application, not just for Azure, but just for cloud in general. Of course, I'll be focusing on Azure-specific features rather than using other clouds. But there's a number of lessons, a number of best practices that you're probably already familiar with that I'm not going to bore you with, like automation is great for cloud development, and reproducibility is great for cloud development. Scaling out, we all know that we can't scale up anymore. It's time to scale out. We've got to test our systems in production. It's not good enough to test in our own environments because what the world throws at us is something that we can't simulate, especially in the tight application lifecycle that we've got today of agile development and pushing things to the cloud. Deploy early, deploy often. This means small incremental updates rather than big monolithic updates every now and then. And that is great for helping you understand where there's a problem, exactly what it is, rather than trying to fish it out of a whole massive bunch of features and changes that have gone into a deployment. But there's lots of other rules, and that's what I'm going to spend the next 60 minutes showing you with real-world examples. These are all actual stories from Azure customers. They're all from the customer advisory team. It's called the CAT team, and this is a team that is part of Azure. It sits in the engineering team, but it's really our interface with customers. If you remember the movie Office Space, they're the guys that sit between engineering and customers. And actually, they do serve a really good purpose in this case, which is to work with strategic customers and interesting projects to understand how they're using our product and how we can make it easier for them to use our product in a couple different ways, by providing architectural guidance like I'm going to be doing here, but also coming back to the engineering team and saying, hey, when they tried to use this service with this other one, okay, so that was probably MSIT doing weird things on my system. They're trying to use this component with this other component that there's a big impedance mismatch. And engineering, you guys need to go add these features and make these connections more seamless. The names of the customers I'm going to hide, except for one case that's a public customer that's actually said it's OK to talk about their name as we go through this. But I'm not going to spend time showing you the details of the names. I will talk about the scenarios, and I'll talk about the actual applications that they're developed and the usage. But if you've got a case that you come across yourself and you're willing to share your name, that'd be great, because everybody likes to see who the real people are behind these kinds of stories. I want to say that this talk wouldn't have been possible without the CAT team. They provided a tremendous amount of support in collecting these kinds of cases and working with me to digest them into the nuggets that would be interesting for an audience like this. And they also helped me produce some demonstrations that will show you with synthetic kind of representations of the kind of not best practice performance that we saw from these customers compared to what you get when you follow best practices. And so I'll be showing you some live demonstrations of that as well as we go through here. So let's get started. This first case is a movie streaming company. It's a pretty big name, although not in the United States. They're a streaming company in Europe, and they started out as a startup about 4 or 5 years ago, and they were one of the first kind of interesting startups that showed up on Azure. And we worked closely with them to make them successful on Azure. In fact, they became successful enough that about a year ago, they were acquired by one of the largest retail store chains in the world, a company called Tesco. And this company right here is called Blinkbox, which does movie streaming. They're based out of the UK. So let's talk a little bit about this case. They started out, of course, born in the cloud, so they went full PaaS. And when you go full PaaS on Azure today, it means web roles, worker roles, Azure database, and Azure storage. And The architecture that they came up with is that viewers would come to the web role. They had WCF protocol between the web role and the worker role. How many people have used WCF? Windows Communication Foundation. How many people like WCF? Really? Okay. Everybody's entitled to their own opinion. So they were using WCF remoting over TCP between the web and worker role. And they built a custom cache inside the worker role to cache the movie metadata. So when a customer would come and say, hey, I want to check out the movies, they would know exactly where to go in Azure Blob Storage to get the appropriate movie and start streaming it. All that metadata was stored in the database, so if there was a cache miss, then the metadata would be loaded from the database. So pretty simple architecture. Now, of course, designing for cloud, you need to design for failures. And one of the failures that they had designed for was, what happens if the cache query times out? What if it takes too long to query the cache from that front end? Well, in that case, they would go right to the database from the front end if it took more than 2 seconds. So let's see what happened, or what kind of problems that kind of architecture produces. The issue is that there's kind of planned failures as well as unplanned failures in the cloud. And one of the kinds of planned failures is if one of those worker roles is getting recycled. And now you've got a load balancer timeout. You're moving between one worker role and that is going down for an update and another one that's healthy. And that starts to cause the front ends that were talking to that worker role in the cache there to start going directly to the database. And what they found is, as they started up and they were doing some loads testing and production with real customers, is that when a maintenance activity, when they were updating their roles or their host OS was being updated, guest OS is being updated, that they would end up making the database fall over. And customers would stop being able to query the movie information. So the solution for this was pretty straightforward, exactly what you would think. They added a cache to the front ends. And that buffered against this kind of back-end timeout. So pretty straightforward case. But again, one of the things I want to emphasize here is that these are real customers. These are real architects like you that are really making real apps. They've gotten to the point where the apps are up and running, and then they run into problems. And at this point, they're sitting here saying, what is the problem? How do I make the performance of this thing better? How do I work around this? And that's when they call in the CAT team. So these are cases where it looks obvious in retrospect, but all of these are going to look obvious in retrospect, and that's really the way architecture works out. When you start with the bad architecture, and you don't understand why it's bad architecture, and then you figure out why it's bad, it's like obvious. And so, again, you're going to, I think, come to the end of this talk and say, okay, I didn't really learn anything, but I hope you do learn something here, because even just looking at a case like this is going to make you think, as you go through your architecture design, oh, I remember that problem that Blinkbox ran into where they didn't have caches to buffer against the case where their worker roles were in the middle of being updated, and so I need to think about that particular scenario ahead of time rather than get the architecture up and running and then run into this in production. This next case is a customer that does election tracking, and they're hired by the state governments to track elections. This was back in 2012, this particular case. The customer created a service to track and report the live tally of the elections at the time across the local, the state, and the national level. And this was being deployed for a very large United States state at the time. And there was 2 elections in that year. One is the September primaries, and they served that one just fine. But as the national election came up, they were concerned about whether their architecture would survive the load. And of course, serving the state election results to the voters was a huge responsibility for them, because voters are looking at what's going on, wanting to understand if their candidates are winning. And if that election site went down, that election results site went down, then everybody's kind of in the dark. The press is in the dark as well. And so they wanted to make sure that they absolutely had everything buttoned down for this national election. So the question was, is the architecture going to scale? And that's when they called in the CAT team just to make sure that it would really scale. And so the CAT team comes in, and here's the architecture that they found. So they've got a whole bunch of precincts that are collecting votes locally, And those precincts are uploading their voting results to Azure blobs. And they're partitioned so that a number of precincts are uploading to specific blobs in different storage accounts. And then you've got a worker role that is sucking from the blobs and sticking the aggregated results into Azure database. Now, voters come in from the front through a load balancer. They hit a web role, and the web role is then querying the database for the results to show them what the results are that they're interested in. So they're going and saying, hey, who's winning in my county, for example. So they also, and this is kind of not material to this particular lesson, but just to show you what a customer like this that is really concerned about being resilient through a major event like this, and actually just anybody that's got a mission-critical application, how you might design your application for disaster recovery, is that they deployed two instances of that same architecture, one to South Central US and one to North Central US. Exactly the same deployments. The only difference is they had a warm failover system here where the worker role in the primary, which was started out as South Central US, would not only dump to the local database for its deployment, but also dump the aggregated results into the database across the country into North Central US. So if there was a problem, they would just simply fail over, and they used Azure Traffic Manager to do DNS failover. And so if Azure Traffic Manager was having trouble talking to South Central US, it would automatically fail over DNS to North Central US. The results would be there, and voter results would pick up where they left off. Each web request in this architecture, as the cat team dug into the code, results in 10 SQL queries. So it's go get the customer, go get the county, go get the voter information, go get the county, go get the results for whatever precinct, go get the results for the national level, a whole bunch of different queries are involved in reporting the results to the user. So the load estimates for the November election that they came up with were an average of 10 million expected page views on average, with a peak in 1 hour of 6 million. So 10 million over the 4-hour time that people would start to look at the results, a peak of 6 million, and just multiplying out the number of database requests they'd see, they came up with about 16,000, 17,000 queries per database that they had configured at the peak. The problem is that the Azure database that they were using scales to only 5,000 connections and 180 concurrent requests with 100 requests per second. A little bit lower than what their projections said. So they said, okay, so we do have a problem with this architecture. We need to drastically change it to be able to handle this kind of load that we're going to see at the November election. So the solution, again, this is another case of caching, is let's put a cache between the front end and the database and make sure that that cache can deliver 40,000 requests per instance, which is how many requests they could get off of a web role talking to a worker role where the worker role was doing local caching. And so this at the time was Azure Cache. Now they'd be using Redis Cache, Azure Redis Cache, to do this kind of caching between the web role and the database. And so now the voters are talking to these caches that are then faulting in from the database when necessary. They can scale it out, each one of these worker roles, and you can see this is the exact topology. 4 worker roles times 40,000 requests that each could handle a second, 160,000 requests. So how'd this do? So that's the architecture they came up with. Looked like on paper would meet the election results. The cat team, so this is the actual graph of the traffic that they saw on election night. You can see that, for some reason my animations got lost, but you can see that at 8 o'clock, that was the peak voting time, they hit 45,000 concurrent requests. Significantly lower than the 160,000 that they'd budgeted for. Plenty of headroom, so they'd planned okay. But when you go back and look at how it would have performed with the original architecture, you can see over the course of that election night, how many requests they would not have been able to serve with that original architecture. In the worst case, 500,000 requests would not have been served. That's those negatives in parentheses. And how did it really do with the cache? This is what they saw, everything in green. This 8 plus 10 seconds with a negative there, that's estimated capacity. That was estimate, that's not what they really saw, but the results spoke for themselves. They were able to handle the load completely. So these were the analysis that they did before and after with the cache. So caching, a great way to boost performance. And let's just show you an example of caching. And I'm going to show you this example that will demonstrate the power of caching, as well as demonstrate some other capabilities that you can take advantage of when you're working on applications in Azure. So what I've got here are two applications side by side. Let me get this so I can zoom in for you here. You can see that this is a bunch of database queries, or a bunch of queries, get customer, get employee, and so the front ends for this particular application, for each request that comes in from a client, is going to perform a number of these different queries, like getting a customer ID, getting an employee ID, and this is the function on the non-cache side. So this is just a straightforward query into the database to get the customer information. On this right side, we've got a little bit of a different architecture. Oh, and I can't see what I'm doing when I zoom like that. Let me show you here. This is get customer right here. And you can see that we've got, let me highlight this code snippet. So this is cached customer repository. And here, we try to get the result from the cache before. And if only if the cache is missed, does it go to the database. And that database hit is then going to result in that query getting cached in the database. So this is the side-by-side comparison that we're going to perform. And what I'm going to do for you is exercise this live. I've got another VM here. And this VM has a load generator configured in it. And let me show you how easy it is to configure a load generator in Visual Studio. So I'm going to go to this no cache example. I'm going to select add, select load test, and then there's a little wizard that will walk you through the load test. And you can see here there's a number of different options. Use recorded think times, use normal distribution. On recorded think times, do not use recorded think times. We're just going to let the normal distribution here. There's constant load. You can also have step load. So if you want to show load ramping up and see the behavior of that, or a constant load, you can base the result, the test mix modeled on total number of tests, on the number of virtual users. So a bunch of different options here. And then you add one or more tests to the mix. So I'm going to add one here. And that gives you an idea. If I pressed OK, we would just be creating a new load test right there that would be able to run against the site. I've already created a couple of load tests, one that will hit both the cached and non-cached load setups here. And that is right here. In the no cache case, what we're going to hit the no cache application with is this scenario right here, a test mix that shows us that we're going to do a bunch of those queries for simulating the fact that for every user query, we're going to hit every one of these methods that's going to end up hitting the database. And one of the things I can show you here is if I select on, if I go to here and select this, one of the other things that you can do is you can see that the cached get customer load test here is hitting your URL. So this is where we've got the app running. And the query here is get customer ID, and then there's an ID here. What we're going to do is, and what I've already done, is configure a random ID. So you specify in this web test plugin, you can specify how you want values to get plugged into the URL. So that ID, for example, we want it to be a random ID selected from our customer database. And our customer database IDs start at 11,000 and go up to 11,376. That's the number of IDs that we've populated in the database. So I'm going to have the load test, whenever it generates a query, fill in that ID with a random value from that range. And that's how easy it is to generate a load test. The other thing you can do is you can have Visual Studio generate the load test, or you can have the local machine generate the load test. Now, I'm going to have the local machine generate the load test. And to do that, I'm just basically going to hit run. So this is the cache side over here. This is the non-cache side over here. We're going to fire up this load test on both sides. And in a second here, a graph is going to pop open. Uh-oh. I haven't seen this error before. Let's see if that rerunning makes that go away. You know, retry is another lesson from the cloud. And there we go. That works. So I don't know what just happened. But whatever it is, we got it working. Now, while that's running, I want to show you something really quick and how easy it is to have Visual Studio generate these loads. Here you can see that when I have the load, when I configure the load test, my local load test configuration says run the load locally. So this are these VMs, this one VM, hitting both the non-cached and cached websites with load generated here. But you can also easily configure it to have Visual Studio generate the load test. And that's going to become interesting here as we look at the output of this result. We've got the two loads firing up here, and the results, which shows us pages per second, and the response time as well of both of on the left side, the non-cached case and the cached case on the right side. They kind of don't look that dissimilar until you look at the scales, which is something that you got to watch out for in these load test results. Because the scale here in pages per second, the range from the top to the graph to the bottom is 1,000. And over here, the pages per second, the range from the top to the bottom is 100. So, and that is this green line here. So we're hitting close to 40,000 requests per second. And over here on this side, we're hitting around 10. You can see the average is 10. So this is quite a dramatic difference of throughput that we're getting between the cached and uncached case. And you can see that the throughput continues to go up as the cache gets populated on each of those database misses. So that's a look at load testing and the behavior of cached and non-cached in front of a database. Kind of obvious. And again, this is one of those things that on a local, small-scale application, you don't typically need to worry about putting a cache in front of the database. The database is a high-performance database. You can scale it up to meet your needs and hit it as hard as you can. Now, when you're in the cloud and you're talking to PaaS database, you get a certain amount of throughput. You're scaling out typically, and like in a case like this, to a larger architecture than you might have designed for on-prem. And so this is where you start to need to worry about caches. This next case is a customer that was basically a lift and shift customer. They had an application architecture that they wanted to move to the cloud. And they said, while we're moving into the cloud, let's modernize it. And this company, it's a company that makes plans for buildings, basically. Plant, civil engineering, spatial infrastructure. They wanted us to leverage all the coolest technology, .NET, SQL, PaaS where possible, and they were shooting for the performance of their existing performance. A common request and a requirement when you're moving to the cloud is, I want at least as good performance as I'm getting on-prem. So here's where they started. Move the ASP.NET code to a web role, move the application logic to a worker role, move SQL to an Azure database. Or, sorry, an IaaS SQL mirroring. So this is a case where they had application compatibility requirements on SQL that weren't met at the time by Azure database, pushing them into this. Now, what they did, they got this. Scale results were disappointing. On-prem, 33,000 counts for a batch test run, total counts. On Azure, 10,000. On an interactive workload, 114,000 was the throughput, 40,000 is what they got on Azure. So drastic difference in performance. That's when they called in Azure Cat. And the on-prem architecture had a combined web and app server. And this inter-role communication that they'd introduced when they moved to the cloud was causing a lot of round-tripping between the web role and the worker role. So they collapsed the web and worker role at that point in time. And the storage wasn't really optimized for SQL usage. So what they'd done was configure storage spaces. This is Server 2012 R2. They used the default striping, the default columns that storage spaces gives you, and they put both of the data VHD and the temp DB VHD on the same storage space volume. And that resulted in this peak throughput that they got of 1,800 IOPS and 15 megabytes per second. Azure Cat came in and said, all right, there's a better way to scale this out. So let's put some more disks under this, and let's get the column count raised on storage spaces, and let's put those separate separate VHDs on separate storage spaces, or on the same, combine them into one VHD, one volume. And what they got here was 5,300 IOPS and 300 megabytes per second. So a drastic improvement just by re-architecting the storage underneath the IaaS disks to better take advantage of the performance characteristics of the IaaS disks up in Azure. And so here's the performance test results that they saw at this point. This is on the far left, what they saw on-prem. In the middle is what they saw on that first architecture with the throughput that I showed you. And on the right is what they got with this revised architecture, collapsing the web and worker role, making the storage space stripes wider, and putting those two databases on this, two VHDs on the same volume, or two databases on the same volume, and they got this level of performance that actually slightly exceeded what they saw on-prem. So a modern application now, with the exception of really the IaaS role, they had web role basically in the front end, so they were taking advantage of PaaS, but performance on a lift and shift application moving to the cloud that matched what they saw on-prem. This next case is a company that it uses hybrid architecture or hybrid PaaS architecture to pull data from lots of client endpoints, mobile devices as well as web browsers, click activity from users, and then feeds that into an analytics system that does targeted ads for those particular users through an opt-in app that those users put on their systems. And they're one of the leaders in this space. And the architecture works like this. They've got local on-prem sources that are pulling this data from devices around the world, putting those into CSV files, and then uploading them into Azure Blobs. And then they're importing that into Azure Database with an ingestion worker role that's reading from the blobs and then shredding those CSV files and sticking those into the database. They also needed a 7-day trailing aggregate view for analytics so that they could understand how they were doing in terms of responsiveness of those users clicking on the targeted ads. And for that, they used HD Insight and Cloud ML to analyze the previous 7 days. So here's the challenge that they ran into when they started with this architecture. The source data, 100 CSV files coming from the different sites that they had, roughly 10 megabytes to 1.4 gigabytes in size of each CSV file. Their average total ingest per day was around 40 gigabytes. So they wrote, this is a huge amount of data to be ingesting up into Azure, into the database. So they wrote a custom ETL process using SQL bulk copy. And the problem was that even with that, the ingest took 37 hours. So if you do the math here, it kind of doesn't work out. So what did they realize? That the Azure database is a scale-out architecture, not a scale-up architecture. So the first thing they did was move the database to Azure Premium, a premium SKU of the database. This is before we had the latest SKUs. This is about a year and a half ago. And this is actually the golden rule right here for getting great performance out of the cloud. Just pay more money and go up to the next highest. I'm just kidding. But in some cases, it is the most efficient way to address the problem. It is just you might be at the low tier of performance of the offering, and that's just not enough to cut what you're shooting for. And so you might need to move up or consider moving up rather than trying to work around the limitations of performance you're going to get at that lower tier and see if you can solve the problem in other ways. Sometimes just throwing money at the problem is going to save you in the long term. They also parallelized the data upload by scaling out the worker role to 8 streams instead of just having one worker role sucking the data out. So they partitioned those blobs by worker role, and now the worker roles are independently sucking data up from those blobs. And then they also, instead of sucking things into the database, they create one table per day in different, well, instead of sticking everything into one table in one database, they created multiple databases, one for each day. So when they're ingesting, they just dump into that day's database, table. And then they've got an aggregator on top that is pulling and aggregating across the previous 7 days. So the next day comes over, once they've got the pipeline full of 7 days, the next day comes in, they toss the 8th oldest day, and then the aggregator runs over the latest 7 days to get that aggregated view that they're going to do the HDN site machine learning on top of. And the result is that with this optimized architecture, the upload took less than 3 hours. And they were able to analyze all of that data and get their daily results for those analytics that they needed. So conclusion on this one, parallelizing. This is kind of another example, partitioning the problem. Partitioning the database, partitioning those blob uploads with those worker roles. And then, instead of just having one giant table of data and then having to go and delete rows that are older than 7 days, partition that also into different tables, because that's your problem, is really it's a daily problem, not a full arbitrary amount of time problem. And so you can optimize your SQL for this kind of solution. This next case is a car company. It's a telematics car company that has services where they pull data from cars and stick it and process it and give users information about their cars, give dealers information about the cars. And what they wanted to do was create a solution on the Azure cloud by leveraging Azure PaaS services. So to do this, here's the architecture. They had an admin web role, and I'm showing you the full architecture here. There's pieces not involved with the direct problem, but just to give you an idea that these are real architectures and the pieces that they make up. They've got a user services web role. That's where users could go get information about their cars. They've got the cars themselves. The cars are pumping data into the cloud using Service Bus. And you can see that there's a bunch of worker roles here that are processing that data. So they've got a message processor worker role that's actually reading the data off of the Service Bus queues. Notification worker role that's got rules based on those messages that the message processor is sending it. So for example, if the car is low oil, maybe that's an alert, and that's a message that came in through the Service Bus queue. And then they've also got a cache as well, and sitting in front of a database where they're dumping information about how the car's performing and its history of notifications. So they did have a cache, but now let's talk about what they saw. Performance measurements showed that it was far less than their target of 10,000 requests per second that they wanted to come from cars. They had a few problems when the CAT team came in that they identified with this. One is synchronous message processing. So if you go back to this architecture, that message processor, although it was scaled out, each one of those worker roles was sitting and pulling one message off the queue, processing it, and then going back and getting the next one. So you got this serial flow of messages going into the message processor. The fix for this one was to have asynchronous or batch receive, so that multiple messages would be delivered in one shot through the queue to the worker role. When it went and did a read from the Service Bus queue, it would get several messages rather than just one in one shot. The second problem is that processing one by one that they were doing. So yes, you can batch it, and that minimizes the round trips to the Service Bus queue. But if you're going to go process those messages serially, you still have a bottleneck there. So the fix for this, concurrently process those messages. Messages come in a batch, fire off processing for each one concurrently and asynchronously. And these solutions, these two fixes that I showed you here, are also relatively obvious, but a lot of people use Service Bus without thinking about these kinds of challenges and these kind of bottlenecks you can create when you use it in the most straightforward manner. Here's a link to guidance on using Service Bus effectively, which includes things like using concurrency and using batching, asynchronous processing like I've shown you here. And I've got an example of how this can dramatically impact processing to show you here. Oh, by the way, yeah. Let's take a look. And this is the serial worker role, and this is asynchronous worker role. Batch worker role is what I want here. Now on this left side, this is reading from the message service bus here, one message, processing the message. Now this is a synthetic app, so the amount of time that it's going to take to process that message is actually coming in the message that the load generator is sending it. So the load generator is saying, hey, here's a message, spend half a second processing this message or a second processing this message, just to simulate that you're actually got real stuff to do on that back end. And then there's a progress tracker that will let us see how fast progress this makes churning through the messages that the load generator is going to throw at it. On this right side, it's a similar loop. Oops. It's a similar loop with one key difference. Well, right here, there's two. One is that we're firing off the message, the processing asynchronously. And the second is that we've configured the service bus queue to give up to 50 messages in each shot. So to batch them up into 50 messages each time that we go read from the service bus queue. Now we get 50 off the queue and fire them off, the processing of them all off asynchronously. So now we can have up to 50 being processed at once. We're on the left side. Each one is done serially one by one. And if we take a look at the load, I've already run this in the load generator. And we've got the results loaded. Actually, here's the synchronous load test, and here's the asynchronous load test. And what we're looking at is the performance. And again, the interesting thing here to note is, oh, I didn't mean to do that. I didn't mean to do that either. I'm trying to, here, get it so I can zoom in for you, is that the scales on these graphs are very different. If we take a look at the average response time for the serial case, you can see that the average is about 20 seconds. And that's because the load test is saying it's picking random load somewhere between 15 and 20. Average response time per second. I'm being told. It's a custom application? What's that? No, sorry. I'm showing you the wrong results. That would help. This is the next test. Sorry about that. I'm showing you the wrong test. That helps. Getting my demos confused here. What I wanted to show you is, I think this is actually on the other VM. Here we go. Here's the back. Here it is. This is an actual live test. Sorry, not the canned one, which is going to be the next one. I've already previewed the next results for you. But this one is the service bus batch versus unbatched. The load test is going to generate 100 messages, give it to the one that's doing a serialized request, and give it to the one that's doing an asynchronous request. I just pressed the button. This is hitting the live production Azure service, and this was to show us the results if it behaves for us. And there we go. Parallel one's already done. All right. So something's going wrong with the serial one. Let's try that again. All right, our serial one seems to not be responding. Okay. Let's try it one more time. This is the risk of doing live demos, is that the demo gods sometimes frown on you and punish you. And well, I guess maybe let's just pretend the serial one is going to take forever because it's so inefficient. And that's the lesson, is don't do it serially. Now, so the actual results here would be that the normal behavior is that this one took, actually, that didn't take 35 seconds. There's something. That took like 3 seconds. Let's try it again. All right, so all right, something really funny is going on with this, because that is like 3 seconds, not 35 seconds. And over here, we should see about 10 seconds or 12 seconds rather than 35 seconds. So something funny going on with that demo. But you get the idea. Batch instead of perform things sequentially. This next case is a company that makes thermostats for buildings. And they've got thermometers all over the place in these buildings, not just one per building, but obviously on lots of different places in the building, in the basement, in the different rooms, in the hallways. And they report the temperature, these smart thermostats, to a cloud service. Now, the cloud service is the point where building managers and the building customers can interact with the HVAC systems in those buildings. So the building managers can look at the results of the thermostats, the results coming from the thermostats, and understand, hey, is the building operating efficiently? Am I paying too much money on cooling? And when the weather, it's nice and cool outside, maybe I got the air conditioning up too high. And customers can go in there and configure where they'd like the heating and cooling to be by looking at the building temperatures that are being reported by these thermometers. This was a big product launch for them, a cloud service to do this at massive scale across all their buildings, rather than kind of having the on-premises deployments they had scattered all over the place. The initial product failed to reach their goals, which was 35,000 connected thermostats. Their target was 100,000. Their stretch goal was 150,000. And so that's when they brought in the CAT team to help them with the architecture. And here's the architecture that they had. Of course, they've got HVAC systems and buildings with thermometers. They've got a building router that is then collecting information. It's kind of a local gateway that's aggregating these temperature results from the different devices in the building and sending them up to a web role using synchronous HTTP. Not that that's a warning right there. Dumping it into a database, and then the worker role or the web role is also processing the temperatures and the other information coming from those HVAC systems and dumping alerts into Azure queues, which would then email alert notifications to the dealers in their on-prem SMTP, using an on-prem SMTP relay. They also had another web role, which was their user interface web role, so customers in the building using their devices could go and look at what's going on with their building and change things. And that was also talking to the Azure database to get information of what are the settings in the building, what's the history of what's been going on in that building. And then I mentioned that they also correlate this with the weather so that the users can understand the weather, and also the HVAC systems can respond to the weather ahead of time as well. If it knows that it's going to be 90 degrees by 10 o'clock in the morning, well, let's start to crank the air conditioner up at 9 o'clock so that it can be still cool when the temperature is rising ahead of time. So that's a quick look at the architecture. And here's the initial performance load test results that you can see. The red are successful requests. You can see that we're getting up to about 1,000 requests per second. And then at the bottom, that far right is an anomaly of the test. And then at the bottom, you also see this low-grade blue line, which are HTTP 500s. Anybody know what HTTP 500 is? Yep, internal server error. So really not scaling well. The biggest issue in this architecture was the one that I flagged for you, which is the synchronous HTTP handler on the front end, talking to those client systems. So they changed that. CAT team came in. Hey, said, let's change this so only the interactive queries are synchronous. Only the ones where customers are actually querying or want results back need to be synchronous. The ones where they're changing things, they're ones where it's ingest of information, those don't need to be asynchronous because nobody's waiting for anything at that point in time. Just drop it in and go. And they were also doing single-row updates to the database. So easy fix to this is to start doing batch multi-row updates to the database to minimize the number of round trips to the database. And they were also using a single low-end Azure database. So the goal here was another example. In this case, they're a little bit more cost optimized. There's some tables that were hot, some tables that were cold. Like building information, that's relatively cold. The stuff you're dumping temperatures into, well, that's going to be a hot table because you're writing into it all the time. So move that to the premium database and leave the cold tables in the lower cost database tier to save some money. They were also preserving XML parameters in the database, which caused a lot of extra processing on the database queries. So they converted those into table value parameters. And then they were using a single Azure queue. And what they did was then switch to a multi-partition service bus queue. That's another example of guidance you'll find on that page, which is to partition your service bus queues. Again, we're in a scale-out world, and partitioning will give you better parallelism and throughput. And this is the updated architecture now. So HVAC system here, you've got the key differences here are those lines, the sync and async results. The HVAC system's processing mostly asynchronous requests, except for the end users, which are getting synchronous HTTP requests. The synchronous reads are coming from the Azure database. You can asynchronous writes going to the database from the worker role, which is also doing write leveling at the same time. And that is the key difference there, is that worker role over there with the service bus between the web role and it, which is kind of buffering the database, and also serving as an intermediary on the weather queries in the email pipeline. So let's see the results. Here's the load test that they ran after that, and you can see that we're scaling up now at the peak above 2,500 requests per second. Those 503s that you see there, those are also just anomalies of the test. So they were very happy with this kind of performance they were getting. And they were able to hit the stretch goal that they had set of 150,000 connected thermostats with the kind of performance they were seeing here after they started to scale this out. So successful case. Now this is where I'm going to show you synchronous versus asynchronous. Response and, oh, okay. Yeah, okay, maybe there we go. So you can't say that I had a demo failure. So here's the synchronous load test, and which you already kind of saw, and here's the asynchronous load test. And now here, I'm going to go back to where I was talking about. I need to show you the code, I guess, for the synchronous and the asynchronous load tests. So here's the synchronous controller, and here's the asynchronous controller. And well, I'm trying to do zoom it, but I can't do that very well through this internet connection. The key difference here is if you look, it's fully synchronous. It's synchronous controller, fake user profile, get user profile. This is all done completely synchronously. And over on the right side, you can see that we've got async here with async await to parallelize all of these requests. And the results of this underload with a synthetic load are as what you see here. First of all, on performance, you can see that we get a very constant level of performance. And this is a response time of 2 seconds. So the response time, which is the average here of about 2 seconds. Over here, you can see that the response time is all over the place. And it's actually going up. And you can see that the average through the whole run was about 20 seconds. So once it started to go up, it's kept on going up. And we had very flaky performance. And if you take a look at throughput, you'll also see another very dramatic difference. Here's the throughput that the load test was able to get. Again, this range here on this graph is 1,000 operations, and over here, requests per second, 1,000. So this is equivalent scale, but you can see that this is able to achieve up here on the high ends of the graph over around somewhere around 900 requests per second. And over here on the left side, you can see that we're only able to get around 80 requests per second. So 10x the performance difference just based on that little change of going from synchronous to asynchronous on that front end, which is one of the, like I said, that key highlight problem of this architecture was that HTTP response handler, which is completely synchronous. So this next one is a smart card application. They do smart card authentication for e-commerce. They had a traditional SOA architecture, web role, cache role, Azure database. So this is an example where they did have a cache. The problem was that the web role would randomly crash. In this case, I just want to, this is kind of just a general how to write a web app guidance. It's not specific to cloud, but again, this interesting case because this company creating this cloud application, pretty serious company, had been in business for a long time, doing smart card stuff. They go to the cloud, they create a web role, and then they run into this problem where the web role is randomly crashing, and they can't figure it out. And they call the cat team. So these random crashes are hard to reproduce, of course. Let's take a look at what the cat team found. This is the actual code that they had in their web role. I'm just kidding. Didn't have this code in their web role. So this, they basically on the button click on the website, spun up a new thread on each one, and the thread would go off and do things. And the thread didn't have a global exception handler around it, so exceptions would pop up, they wouldn't be handled, and now not only does that thread fault, but the whole process faults. And this thing is running inside the same process as this code, the handler, so the web role crashes completely. So the other problem that they had was that if the backends went down, because this synchronous processing on these different threads, all the threads start to get piled up because they're all busy doing stuff. And every one of these requests generating a new thread. And that also can lead to exceptions because you can run out of memory. And you also get into resource starvation. If the threads all start to wake up at the same time, now you get CPU spikes, and now the front end becomes completely unresponsive. And then it has that other problem that I mentioned of the exception handler not being there. So the resolution of this one was they moved the worker logic to a worker role and connected the web role asynchronously through service bus queue, in this case, Azure storage queue, to the backends. So decoupled the front ends and the back ends, and of course, put in some resiliency around these kinds of faults. This next case is a company that does contract management software. So kind of contract workflow software. This is their architecture. Front end has a user interface, has a REST API on it. Middle tier also has an API that the front end talks to, has business logic, some workflow in it. And then the worker role does batch processing on some of those workflows. They've got storage for where they're putting those contract files, and they've got metadata and reporting on the contract workflows that they stick in an Azure database. They've got a lot of chatty APIs. So those APIs between the front end and the middle tier, that's a chatty interface. And they also have a chatty interface to the database, like we've seen before in some of these other examples. And also, a couple of other issues. They're doing XML processing in T-SQL as they stick things into the database, because they want things to be in the database in XML format. And they're doing OLTP queries on the database that they're also dumping those results into. So a few problems that they ran into this. Chatty database calls at a page load, at a contract load, OLTP and reporting on the same database interfering with each other. So these OLTP queries, which can be long running, those don't have to be instantaneous as people are doing these kinds of queries, interfering with your more real-time dumping of data into that database. They're also generating the metadata as XML on the database itself. And then they've also got a storage procedure that's also doing string processing on those XML queries, which is also putting more load on the database as well. So a whole bunch of problems. So let's just avoid the database where we can. They moved the string and XML processing on to the middle tier. They moved the reporting to the geo-replica. So one of the things you can get with Azure Database, you get this for just disaster resiliency, which they wanted, is you get copies of the data copied to a second instance in another region. So, and you can do reads from that. So that's a great place to do your OLTP. It's a separate instance of the database. Your writes are going into the primary, and your reads are coming off the secondary and not interfering with each other. And you're basically making use of money that you're paying for that second database instance. They changed to a single query where they could on the front end those REST API calls. They consolidated some of those calls. On the back end, consolidated the SQL queries into a minimum number of queries, and what they saw was 10x performance improvement. And this is the updated architecture. So chunky IOs on the front, XML processing in the middle tier, and reporting at the geo-replica rather than at the primary. And I've got an example here of a load test on a synthetic app that does exactly what we were just talking about. So if I go to, what's that? Oh, go to the browser again. I thought I had a code sample for this one. Yeah, and actually, this is, oh, it's in the project. This is right here. It's tough to keep track of all these demos. Here we go. So we've got this busy database example, and we've got the query in SQL. Let me show you the SQL query. So this is a SQL query that's doing a whole bunch of XML, which is actually not what you want at all for performance. And here's the controller for this, which is simply doing basically one SQL command and just waiting for it. So very simple kind of controller, because all the work is being done in that SQL query that we saw back here, this complicated code, which is doing this kind of XML. And if we take a look at the query on the one where the processing is done on the middle tier, here's the SQL query. It's a lot simpler to understand. It's a lot less resource intensive on SQL. And if we took a look at the controller, well, that work moved into the controller itself. And you can see here it building up the XML that it's going to be putting into that query. And that's where we've got this load test here. So this is XML processing in the database layer. This is hitting that left side example. And on the right side, we've got hitting that right side example. And you can see 10 queries, XML on the database versus XML in the middle tier, the kind of performance difference that you're going to see. A drastic difference with that simple code that you saw right there causes this kind of drastic difference. In fact, in this customer's case, here's the example of the throughput that they saw on the database. So the load on the database here on the busy one, this is actually from this synthetic query that we just saw, but very similar to what this customer saw. Like I mentioned, 10x performance improvement they saw. XML processing in the middle tier versus on the app tier, the load on the database went from 87% down to 37%. So lots more headroom for lots more real work on that database rather than the stuff that they should have been doing somewhere else. And we got one last example here. It's photo sharing application. So a company is doing photo sharing and image processing in the cloud, offering customers unlimited storage. The first release had a limit of 50 requests per second. Their target was 7,000 requests per second. And here's the problem. This architecture right here. Everything in one web role. So hey, let's go to web role, let's go to PaaS. Then they created all of these services inside the web role with one database on the back end. And they also, here's another key thing that they got wrong, is that for every one of these queries to these other services, they were using a different HTTP request. They were actually using HTTP in between these things because they'd migrated them from another architecture where these things were using HTTP. So just a horrible, horrible architecture, but a real one that they called the cat team in. And so the cat team refactored the architecture into separate web and worker roles. They changed my builds out of order, but they changed the asynchronous calls across the architecture. They actually optimized for storage. Instead of sticking all the pictures in the database, they stuck them someplace else. And this is now where you see what's going on. Image processing goes to blob store. You see the cache being stored, a durable cache being stored in table storage, and then you see a cache in front of the Azure database. And you also see that they're reusing HTTP connections as they talk from these one service, which now is in the separate web role, to these other web roles, which have their own dedicated services. So big difference in the architecture, and let's go take a look at an example of that in Visual Studio, and I'll show you the results of this as well. So here's new HTTP request per control. Pretty straightforward. You see HTTP client, new client request per each request. And on the right side, you see single HTTP request per client here. And that's demonstrated by this fact right here. You can see there's one HTTP client that's just simply being reused on every one of these requests here. And also, we see asynchronous processing. And so let's go take a look at the results for this. And pull this up here. Here's the throughput for performance for the one where we're creating a new request for a new HTTP client request for every one, and the one we're seeing for asynchronous reuse of the same HTTP request HTTP client. And you can see the average response time here. Average is around 1.2 seconds. Average response time here is 0.2 seconds. So 6x difference in response time. And we'll see the same kind of benefits on throughput as well. Again, if we're taking a look at requests per second, you see the scale here is 10x what the scale is over here. 1,000 is the scale over here. 10,000 is the scale over here. And the request per second goes up to about 3,000. And over here, it's hovering at around 600 or so. So massive difference just from that simple code change as well. So that brings me to the conclusion of the talk. And here are the kind of lessons that I hope that you took away from this. Cache aggressively. Always worry about caches, local caches, caches between your database, caches between your web and worker role where you can. Asynchronous processing with queues where possible. Process in batches, minimizing round trips between your various tiers. Partition your data and compute to take advantage of scale-out architectures. And then use the database for database work, not for other work. And take advantage also in your database and other places where you can of those secondaries that you've got, which you can also do processing from. All of these cases are available right here at this GitHub repository. This whole project is, so you can go look at these examples and play with them yourself. And then there's another GitHub repository there that has a bunch of other architectural design patterns that you can follow. Both of these have been created from the CAT team. And there's documentation here. I actually pull this up in the browser just to give you an idea of what's here. And then I want to leave you with one last freebie for everybody in the room, which is how many people here are working on a real project right now where you'd like some architectural guidance? Okay, I'll give you everybody in here something free in a second. Here's that page. So this is the page with this project that has all these examples on it with documentation about what each of them do. Now here's the free thing that I'm giving you all. The CAT team is here on site. Here's where they are. They've got a CAT clinic. That's the map of where you can go find them. They're here during conference hours every day here through the end of the week. You can go down there, take them your architecture, tell them what problems you have or what guidance you want, and they'll sit down, understand your project, and give you that guidance, all completely for free. So I encourage you to take advantage of that and have a great rest of the Build conference. And I'll hope to see you next year. Thanks.